Welcome to the second session, the open public panel discussion section of our seventh dialogue in biological anthropology here at Boston University. And today's dialogue is on the origin and significance of the use of fire by human beings and how far back it goes in the archaeological and paleontological record. And I'm very happy to be joined here today on the panel by my colleague on the far right, Professor DeSilva of our Department of Anthropology here at Boston University, by Professor Francesco Berna, who has also been a colleague of ours at Boston University and is now, to our sorrow, going to be leaving us for Simon Fraser University in British Columbia. And on my left, Professor John Shea from Stony Brook University, who is a world-famed and extremely both articulate and diversely knowledgeable archaeologist with a specialty in Paleolithic archaeology. And so what we're talking about here today, as those of you who had the opportunity to watch our webcast earlier this afternoon know, is the evidence for the early use of fire and for the significance of the onset, the advent of the use of fire in human prehistory. I thought I would begin this panel discussion by just saying a few brief words about a topic that was mentioned in our webcast, but that we didn't really have an opportunity to talk about or to elaborate on, and that's the cooking hypothesis that, among other people, and most notably Richard Wrangham at Harvard, have been elaborating in the literature and in books and public lectures over the course of the last several years. Briefly, the cooking hypothesis suggests that the use of fire was not only important in the obvious ways to human prehistory, to facilitating the movement of humans and our ancestors, the early species of the genus Homo, out of Africa into temperate and cold climates, into higher latitude parts of the world, and to permitting us to cook our food and to scare off wild animals at night and change our activity patterns so that we can stay up all night if we want to, and so on, but that it was in fact instrumental in bringing the genus Homo itself into existence. And the argument runs something like this. Humans are, of course, the only animals who cook food. And until fairly recently, I think the general assumption had been that cooking food is nice and everybody likes cooked food because it tastes better, and sure, it's easier to digest and it does various things for you. It kills off the germs, it kills off the parasite eggs and whatever you're eating. It breaks down the proteins and makes them more digestible. But the cooking hypothesis holds that it's got an even more fundamental significance than that in fact we not only prefer our food cooked, but that we can't eat non-cooked food as a steady diet, that a raw food diet is simply something that is biologically impossible for human beings. And this keys into an earlier hypothesis developed back in the mid-1990s by Aiello and Wheeler, which is called the expensive tissue hypothesis. And the fundamental fact here in this notion, the Aiello and Wheeler hypothesis, is that, as we all know, human beings have rather large brains. We don't have the largest brains in the animal kingdom, and we don't even have the relatively largest brains in the animal kingdom or the class Mammalia. But for our size, we have larger brains than any other animal. And in particular, we have larger brains than the animals that we're most closely related to, the great apes, which are, very brainy animals as mammals go anyway. But, even though a chimpanzee is a very smart mammal, an adult human being has a brain roughly 3 times the size of an adult chimpanzee. So the question is, what does this mean for general human biology? Of course, it means that we're smart, but it means some other things. And Aiello and Wheeler examined the relative size, the contribution in percentage of body weight to overall body composition of different organs in different primates. And they found, sure enough, that human beings have disproportionately large brains. But they also found that human beings have disproportionately small guts. We have very little in the way of intestines for an anthropoid primate. You'd expect us to have much bigger guts for an animal of our body size. And the contention that was made here was that this was a trade-off, that human beings were able to have large brains and everything that goes with it, because we ate high-energy diets and processed them in an efficient manner that meant we could get away with having much smaller and cheaper digestive apparatus than our great ape relatives who eat diets composed almost exclusively of plant material and, to a large extent, rather low-nutrition plant material, stuff that's high in fiber and not very high in calories. Okay, so the cooking hypothesis holds that not only is this true, but that what's especially important about humans is that we cook our food. We digest it before we put it in our mouths. And that's one of the reasons we can get away with having such small guts. And it's one of the things that frees up a large chunk of our energy budget so that we can invest it, take away from the investment in gut, and put it into an investment in large, calorie-hungry, glucose-devouring brain tissue. Okay, so the antiquity of cooking is a very important part of this story, and the problem is that the genus Homo dates back about 2 million years, but nobody has ever found any very convincing evidence for fire going back more than about half that period of time, about 1 million years into the past. And so there's a continual tension between the kinds of things that some biological anthropologists like Richard Wrangham and Aiello and Wheeler want to say about human brain and gut evolution and its relationship to cooking and the sorts of things that the archaeologists are able to tell us about fire. So that's a very brief and probably incomplete sketch of the cooking hypothesis. I'd like to ask my biological anthropology colleague, Jeremy DeSilva, if there's something he'd like to add to that.
No, I think that was a pretty good summary of the cooking hypothesis. I hadn't thought of it necessarily framed with the Aiello and Dean expensive tissue hypothesis the way you just did. But the problem, of course, and the challenge is reconciling the time differences. That the origin of genus Homo certainly does go back closer to 2 million years than any origins of fire do. And the question that I have is it simply because we haven't been able to detect this in the record, or is this a real signal? And I guess that's something that Professor Shea or Berna should be answering.
You guys?
One of the problems with that time range between, say, 1 million years ago and 2 million years ago is that the archaeological sample is very, very small. If you spread out the area that's been excavated by archaeologists during that time range, you might cover 2 floors of this building total. And you're talking about the behavior of a species distributed on 3 continents for 1 million years. So it's very, very small. It'd be like trying to describe what modern-day Boston is like by sinking a test pit in the parking lot behind this building. So I think it's a credible case to be made that it's sample error, that the evidence looks weak because we don't have much evidence. But that's one of those hypotheses you test every time you put a shovel into the ground or a pickaxe to rock. So environments like Wanderward Cave that have wonderful preservation, that are sheltered from the kinds of open air processes that degrade the record of fire traces. These are unique windows. They're high quality parking lots, if you will. They're places where you look where the light is good. But I mean, if you can go to places today in Africa, where like Turkana, where I work, there are people. We know there are people using fire. We see their fires at night. You go to their sites within a few weeks, and there's not any evidence whatsoever that they were using fire. So it's a known unknown, to wax Rumsfeldian.
Let me ask you two archaeologists a question. Given that there's evidence that Homo was out of Africa for almost 1 million years, before there is any conclusive or even very persuasive evidence of people using fire, is there any reason to think that the use of fire had a single geographical origin?
No.
Okay.
No. This is the problem with researching this researching human prehistory as an historical phenomenon. You end up with these simple anthropogenic models, and somebody comes down from the tree and they eat a can of spinach or something, and it makes them human. These are stories. These are mythological frameworks, like the ancient ones about Prometheus or Raven, the Inuit hero. These aren't scientific explanations. Scientific explanations need to embrace the true complexity of the phenomenon. It's possible people invented fire for many different reasons or reinvented it many times. That just doesn't make for a simple story.
I've got a lot of questions here that were sent in by some of you, and those of you who didn't send in a question will have ample opportunity through most of this hour to ask the ones that occur to you as you listen to other people's questions being answered. But I'd like to get to some of these other people's questions. And I'd like to ask something of Jeremy that came up in our discussions this morning. One of the things I forgot to mention about the cooking hypothesis is the notion that if you cook food, you don't need to chew it as much, hardly at all. Okay? A chimpanzee spends something like 6 hours a day chewing and chewing and chewing, picking up these dreadful, fibrous fruits with practically no sugar in them, and chewing them and chewing them and chewing them and spitting out the pulp and doing, humans spend maybe half an hour a day chewing. It frees up an enormous amount of time, but more importantly, it means that we don't have to have the kind of chewing apparatus that a chimpanzee does. And so one important part of the cooking hypothesis is the notion that with the advent of cooking, the genus Homo was able to evolve smaller teeth and smaller jaws and smaller jaw muscles than we see in apes of similar size. Here's the problem I have with that. A number of the features that distinguish early Homo from our more ape-like ancestors in the genus Australopithecus, the bipedal, quote, man apes of southern and eastern Africa. One of the things that's peculiar about Homo, some of the things that are peculiar about Homo seem to be primitive. The Australopithecines have huge molar teeth, and early humans have rather small ones, but they're no bigger than the early Australopithecus. In other words, and humans have rather small jaw muscles, genus Homo humans, but again, the jaw muscles aren't any bigger than what you would see in early members of the genus Australopithecus. So in these respects, early humans seem to be primitive, and yet these features are being described in the cooking hypothesis as specializations that are made possible by the control of fire. Jeremy, do you
Well, I mean, so you've got two different ideas here. The first is that the ancestral condition is the small-toothed, small small temporalis muscled animal that's not doing much chewing. But then a lot of the Miocene apes, a lot of the fossils of the Miocene apes look like they have some pretty significant masticatory apparatus there. Even the early Australopithecines, I think Anamensis looks like it has decent-sized teeth and some nice musculature as well. But the question that I think we're struggling with in our field right now is if you go back into the Pliocene, if you have multiple taxa in the Pliocene, which Afarensis has always been the only game in town in the Pliocene, but Kenyanthropus platyops has been described by Maeve Leakey and her team as a smaller toothed alternative to Afarensis. And so we have this possibility where over the course of human evolution, teeth started relatively small, got big as Australopithecines were beginning to live in a more terrestrial environment, eat more difficult to digest foods, and they evolved larger teeth and a more robust craniodental musculature, or cranial musculature. And then as we invent stone tools and cooking and so on and so forth, the teeth begin to get smaller and off we go. There are some other specimens from the Pliocene that Maeve Leakey and colleagues have found in Kenya that suggest that there was a smaller toothed thing living at that time, and that maybe the Australopithecines of that time period, like Afarensis, should be pushed to an extinct side branch and are ancestors of the robusts. So I think this is one big interesting challenge in our field right now, is to know how many different lineages existed back then and which are the true ancestors. And frankly, we don't know. I don't know.
I've always had a question about this idea that the fire, the tool use, ends up causing teeth to become small. Because it always strikes me as it doesn't. Okay, forgive me, I'm an archaeologist. We're simple people, but it strikes me that if you relax selection, what you ought to get is variability, which ought to enable smaller toothed individuals to persist, but also enable the growth of larger teeth. You ought to see once you see stone tools or fire as aids to cooking, you ought to see an increase in the variability of tooth sizes, not necessarily a trend towards smaller ones. Mm-hmm. Maybe something else is driving selection for or against.
Maybe that explains this problem with the origins of genus Homo, where we've got Habilis and Rudolfensis and all these different kinds of habilines, and a lot of that is based on tooth size, right? Rudolfensis has big teeth and habilines have the smaller ones. Maybe we're just seeing increased variation.
No, but that increased variation, if you're looking for consequences of fire, that's a conceivable one, is it would free up variation, and that might be the predictable anatomical consequence of use of fire far beyond our ability to detect it in the archaeological record.
But you know, this is a pervasive question in evolutionary biology generally. When things become useless, they tend to shrink. And the usual explanation is, oh, well, it uses less calories that way if you don't make big teeth. Well, you know, I think the number of calories it takes to make a tooth a couple of millimeters larger in each direction is probably equal to the number of calories that I would get by running up and down the stairs a couple of times in this building. And I don't really think it's going to have a measurable selective effect on my probability of growing up and having offspring. So I've always been puzzled by that. Loring Brace used to have this old theory called the probable mutation effect, where he said basically if you hit a watch with a hammer, the chances that something will stop working are greater than the chances that something new will start working or that it'll work faster. The idea being that if there's no selection controlling for mutations, that mutations that make things smaller and tend to disappear and not develop properly are probably more likely than ones that make them bigger, and that by itself might be sufficient to explain this general, it's almost universal trend towards the disappearance of unused structures in evolution.
I would add that also to pre-digest food, you don't need to cook it. There's other strategies like fermentation, aging. So it doesn't really go logically one to the other.
Okay, with that, why don't we open up the floor to questions from the audience and see what people want to know about and what their ideas are. Any questions? Our volunteers are standing by with microphones.
This is the first I've heard about the cooking theory in the evolution of the human brain, basically. I wonder if you could basically link it to if you could tell me why the cooking theory would, say, make more sense than previous theories such as the bipedalism theory. That as the theory goes, that brain size was linked to bipedalism because, say, the structure of the pelvis would have to develop, and thus the structure of the brain would have to develop after birth because of the size of a birth canal. That theory was, of course, bunked when we saw that humans were becoming or hominids were bipedal long before we started developing larger brains, but with no evidence of, or with very little evidence of cooking, or with very little evidence of use of fire until we basically evolutionarily become the species that we are, how would the two theories really connect? I mean, is there any reason to believe that perhaps certain anatomical and structural changes might have brought on the advent of cooking, the advent of experimenting with fire before the use of fire became widespread?
I think on the bipedalism issue, I think you may have the arrow of causality pointing in the wrong direction. The usual thing that is said is not that bipedalism causes big brains, but the reverse, that bipedalism makes it difficult to evolve big brains, and that is bipedalism of a humankind, because there are opposed constraints. When you're bipedal, you stand vertically, and abdominal pressure tends to be concentrated at the bottom of the abdomen, just as pressure is concentrated at the bottom, say, of a carton of milk. Because the stuff at the bottom is carrying the weight of all the stuff at the top. And so you tend to spring leaks down at the bottom, like inguinal hernias and visceral prolapse and so on. So you want to keep that opening small. And that means that if you want to get a big brain, you have problems getting the big brain at birth out through the small opening. This is the kind of constraint or the kind of causal linkage that has usually been posited between bipedality and big brains, namely that bipedality makes it hard to evolve big brains, and so what you have to do is get born with a fairly small brain and do most of your brain growing after birth. This happens to, however, be a specialty of Professor DeSilva's, and he may have some specific and maybe even challenging comments to make about this.
Well, I think, as you mentioned, bipedalism precedes brain increase by several millions of years, and so that hypothesis has been falsified. But that's where fossils become incredibly important. It's a reasonable idea to compare humans to chimpanzees, say, well, we walk on two legs, they don't. We have large brains, they don't have them, so let's develop an explanation for why we look the way we do. And then how do you test it? Well, you need some physical evidence. You need some fossils. So in Darwin's time, when there were no fossils whatsoever, a couple Neanderthals, I suppose, these were reasonable ideas floating around, and you test them with fossils. And we know now that the fossils have shown that that's completely a problem. Now, when it comes to the cooking hypothesis, I find it to be a really elegant and well-conceived explanation with tremendous explanatory power for why we are the way we are. The problem is the timing. That if this is what's driving the evolution of genus Homo, we should find fire a lot further back in time than we actually do. And maybe it's a problem of actually finding that evidence, because if, as John was saying, campfires that you know existed can't be picked up just weeks later or something. Maybe our standards for finding evidence of fire are too extreme. Which actually, that I want to ask a question about that. How do you balance this problem of saying that a 2 million year old hominid made fire would be an extraordinary claim, right? And extraordinary claims require extraordinary evidence, and yet you can't even detect fire that was made a couple weeks ago. So shouldn't our standards of evidence be dropped down a little bit? And any hint of evidence for fire would actually be pretty good evidence.
Well,
You know what I mean? How do you balance those two
Depends
things?
on your tolerance for false positives. And it's not the case that all recent fires are indetectable. It's the little fire that a few shepherds might make, this will get blown away by the wind the next day, whereas the campfire over which they've cooked food for weeks on ends at a Turkana campsite, that'll be obvious. You'll be able to spot that. But there's variability in these hearths. The longer they're in one place, the easier they are to detect archaeologically. They form distinctive traces, they're rejuvenated. Some of the methods that Francesco talked about, you can apply them and it's clear. You've got multiple layers, you've got cross-cutting and recharging of the hearth with fuel. A little campfire where you just got 3 logs together, overnight with 3 stones between them, unless those stones between them remain, you're not going to have much trace of a Turkana fire. So you have to have that potential false negative thing in mind, just as you do the possibility of false positives.
But I think if you look for this evidence at a microscopic scale, you have more chance to find, little bits of wood ash in cracks that's being protected. So it's, we're dealing with a very, very difficult issue here. And, and a lot depends on the characteristic of the site that you're gonna end up. And I'm sure there wasn't much done so far in very early hominin sites. Looking at sediments at this scale and looking at, mapping. So.
John, you were saying when we were talking this morning that there's a difference here between cave sites and open air sites, in that in an open air site out in open country, there's no particular reason for building the fire here rather than over there or over there. But inside a cave, there are definite reasons for wanting to put the fire exactly there and not 10 feet away in either direction.
So caves increase the chance of a temporary fire being positioned in the same place. I mean, if we imagine where we're sitting right now is a cave, flanked by stone walls here, the place to put, and the drip line was where these lights are, the place to put the fire would be about 2 meters in front of the backdrop here, so that we would get both, broadcast of light out in front to deter any carnivores, as well as some long wave radiation back, hitting us from the side and then warming us from the back. And when you excavate cave sites, there is this regular pattern. People put the hearths, 2 meters or so in front of the back wall of the cave, or if it's a deeper cave, they put it fairly close to the opening, so you get the smoke, exfiltrating the cave. You don't want to breathe in the smoke, and you get some broadcast of light to deter predators, but you also get some radiation wave back into the cave for warmth and for other purposes. So it's, looking at caves enhances the chance of finding it, but there are very few caves. Caves are not long-term phenomena on the landscape. You don't find a lot of caves in the millions of years old, which is why wonder work is really important. Of all caves we know of, this is one of the oldest caves.
Yeah, and it's an outlier anyway, because those very few sites are in caves that old.
there are probably many caves that are deeply buried as yet to be discovered. I mean, I guess some in Israel, they found it when they ran a bulldozer across the top to build a highway. So you also need to increase archaeological methods for detecting caves that are now completely buried.
Yeah, exactly.
That's a problem where our geologist colleagues can help
Yes,
us.
exactly.
Lee Berger is claiming he's got techniques. I don't know if you talked to him about it. And I don't know.
Finding caves. Yeah,
Yeah,
there are all
for finding
kinds of
caves.
techniques for subsurface radar that are being deployed in the service of this question now.
Yeah.
So are there any caves then that you employ this sort of logic of this is where the hearth should be? There are hand axes littered along the landscape, so we know hominids were here, or they're butchered bones or something, but we just don't find any evidence of fire. Are the caves like that? Or is pretty much every cave that's been studied?
Every cave I've seen has fire and start from modern time going down. So there's also because some cave deposit can self-ignite because, the accumulation of, so there is fire in many caves. So the problem is, how you determine a specific fire you're dealing with is anthropogenic. And the second problem is this like an occasional fire that, or is, people that did that fire knew to light a fire wherever and whenever they wanted. So that's not easy to answer.
This provides me with an entry into a question that was sent in fact, a whole flock of questions that deal with the difference between being able to use fire once you've got it and being able to make it.
Yeah.
Okay? And I think it's a lot easier for many of us to imagine some of these early Homo species being able to use fire, to even to keep fueling it, and to cook things on it and warm themselves around it, than to make it. We know chimpanzees can be trained at least to use fire in some of these ways that would have been useful for early Homo, but they have no idea how to make it. So I might like to pose the question of how do you go about making fire? How difficult is it really to make fire? And I'm posing this question with malice aforethought because we have a demonstration of how to make fire, which Professor Shea has been kind enough to bring along. Professor Shea, I should mention, in addition to being a highly erudite scholar of archaeology, is also a mean flint napper and has a whole bunch of Paleolithic technologies at his fingertips. And so we're about to see one.
All right, well, the most common way of making fire, I'm going to be transitioning between the suit professor role and the primitive technology instructor role here as I talk. The most common ways of making fire around the world are by friction. So friction of different kinds of woods against one another. Most of you have probably heard of flint and steel, collision product fire. And that can be done. It's pretty tricky. All of these methods require a lot of training, a lot of expertise, and a lot of practice. So even under the best of possible conditions indoors here, I'm not going to start a fire. I mean, the last thing I need is, here's your bill for the building it from BU. They don't give alumni discounts. Anyhow, for making fire, the simplest possible method, one of the most widespread methods. First off, what you need is something to catch the burning material. So 2 parts. What you need is we call a pan, a bit of wood. And second thing, of course, you need is fuel. And this is a bird's nest, a little nest from the backyard. Dried out. So what you want is fuel with lots of surface area. You want this thing to burn like that when the spark gets into it. You also want something that will burn slow, so in this case, birch bark, which basically can burn completely wet. Now, this bird's nest, I've dried it out, I've opened it up, and I'm not going to actually kindle the fire, but what you need is something like this to catch it. The it in question is a spark. So we're going to put we call it the tinder bundle off to the side here. And you need a surface onto which to bring superheated sawdust, basically, or char. And the whole business of friction fire is you're rubbing 2 sticks together, basically, in different ways to create superheated charcoal. The second component is something we call Fireboard. This is a soft bit of wood. This one's pine. You'll smell it here once it starts to hit the ignition point. And these holes here are little holes we dug into it with a little notch at the side through which the superheated char will drop onto the pan here. Now, there's several different ways of doing this. I mean, the main thing is to keep this thing from moving. So I'm going to plant my leg on it. And the simplest method is the one that will take the longest. Using a bit of wood here, this is soft, this is a yucca stalk. Place this into the depression. Hold the
Friction.
grip there to prevent my hands from sliding. And then what you do is you start rotating, bringing your hands down the stalk gradually. I'm trying to put a lot of energy on this, but as you can see, my hands migrate down the stalk. I'm getting a little bit of smoke there. And it takes a lot of time, it takes a lot of work. I can smell a little bit of char being generated here, but this is going to take me a lot of time. And I'm lazy, so I want it to work faster. That's another trick, is to prevent the slippage of your hands. Make a little notch in the top of the stalk. Put a little bit of fiber in there with 2 little loops on the end. Put your thumbs through these things. This prevents your hand from sliding down. So, yeah, what you want to do, get your center of gravity over this thing and start moving your hands. What's happening here is little bits of sawdust are falling on the pan, but only little bits. So now, if we had infinite time and I had infinite strength, we could do this all night. Eventually, something will get lit. The fire department will show up, and I'd be getting a bill for the oil center.
I can testify to those of you who are sitting in the back that we can smell burning
Smell.
wood up here.
Now, the faster way of doing this is to use bow drill. What you have here is a bit of leather all plated back and forth, so it's really tough fiber. And just an old stick, a little bit of willow stalk here, and a bit of pine wood. Wrap it. Oops. It's always the tricky part. You want to get this fiber around the spindle, the turning piece. Put the turning piece into the hole and put a capstone over it. Again, get your center of gravity over this thing. Everything you don't want on fire out of the way. And start slowly. Then with ever longer strokes, you reverse the spin of the piece in the hole. Get the camera on this real close. I'm only going to get the smoke going for a short time. You can tell it's ready to go right about the point where you start choking on the smoke.
Oh, wow.
Okay. And yeah, it's right there. Now, the bit of, yeah, it's still going. But let it die out a bit. The next trick, what you do, would be to drop this into the tinder, get the tinder up above it, blow lots of air into it. You're going to get oxygen into the heat plus fuel, and eventually it'll pop into fire. And then I'll yell, my hand will be on fire, and I'll run out in the street. So that's, I think you guys who are up front can smell, but I stopped. I usually, to make this, I would keep going until I could barely breathe. Turn 3 gulps of air, and then pop it into here, and it'd be good to go. So, as with any such thing, it's good to have multiple solutions to the same problem, and so I've just taught you 3 of them.
Thanks, John. So now that we know how to make fire, or some of the ways to make fire, the best ways to make fire, the question that occurs here is, can you imagine a phase in the human control of fire in which early Homo had the ability to utilize fire and cook with it and heat with it and so on, but did not have these, to my way of thinking, fairly sophisticated technologies? You know, that last one is pretty clearly related to the bow and arrow. These fairly sophisticated technologies that are needed to start fire, and if not, then what is life like? What might early human life be like in the absence of a means of starting fire, where the only way you would have of getting fire is either borrowing it from somebody else next door or waiting for lightning to strike. Is this possible? Is it even feasible?
Well, one perspective on it from this is that it does take a lot of knowledge, it takes a lot of practice, and if you lose it, I mean, I can't imagine the worst situation to be in would be to be aware of fire's utility and not have it. So if you think about it in terms of forming bonds among, earlier humans, the gift of fire from someone who has it to someone who lacks it, or the gift of showing someone how to make fire. Like they say about teach a man to fish, he'll fish forever. It's probably an important factor in early human social evolution, plausibly. I mean, I don't know how to prove it. But.
I should mention the variant of that adage that occurs in one of Terry Pratchett's Discworld novels, that if you give a man a fire, you'll keep him warm for an evening, but if you set him on fire, it'll last all his life.
To your question, I think one thing we could do is look in Homo erectus industries, or old one or later, and find evidence of knowledge how spinning, friction, drilling, and for my knowledge, it's not so obvious that Homo erectus was able to do that. And so also like circular structures, like circular symmetry in
Evidence of holes drilled in things. I mean, you get this in Neanderthals.
Yeah.
But John, you were saying that isn't being done using a rotatory drill technology.
Now, the evidence for rotary drilling like this doesn't show up until very, very recently in the archaeological record. But there are other ways, not involving rotary drilling. The old, rubbing two sticks together is a cartoon, but what it actually involves is actually a stationary bit of wood, another being moved back and forth across it, or another piece of wood being moved like a saw back and forth across the fire saw. That's no different than slicing with a bit of stone. And that sort of fire saw technique, very popular in Polynesia, very popular in Australia, and I think it occurs elsewhere as well. That doesn't require any greater mechanical sophistication than being able to drag an edge across something. Something for which a technological process, cutting, for which we have stone tool evidence going back 2.6 million years currently.
So let me once again turn to the audience and ask those of you who are out there who have some questions to ask them.
Regarding the same question, would there be any possible way to infer this difference between the making of fire and then just the controlling of pre-existing fire from the archaeological record?
I think you'd have to discover evidence of the production technology. And while there are sites in which wood is preserved going back in excess of 700,000 to 800,000 years, the oldest evidence for this wooden fire making technology is all very, very recent. It comes from dry caves 2,000 to 3,000 years ago. I think there's maybe a few older ones in Europe. There are little strikolites, little bits of flint and pyrite that go back maybe 25,000 years. So collision product ignition. That has a little bit, very barely Pleistocene antiquity. But this technology is really, really subtle. The only reason you can detect it at all is this is a kit I carry around in which I do multiple demonstrations. If I was doing this on a desert island and did it once, that would have zero visibility.
So all archaeological evidence, either for fire-starting technology or for other technologies that are organically related to fire-starting technology, like rotary drills or strikolite kinds of things, those are all restricted to anatomically modern Homo sapiens.
Yep.
Okay. Other questions?
Mine is kind of more for the anthropology side. I'm wondering if to make more narrow the gap between the cooking hypothesis and sort of the big brains, are there any other anatomies that have changed sort of in terms of the gut? So are there any like balancing mechanisms that we see, or like foot morphologies that kind of have to accommodate for a larger gut or for a smaller gut in that sense?
Not that I'm aware of. That's a really studied area as far as I'm concerned. First, I don't think we actually have good evidence of how large the guts were and how it affected the mechanics of walking, if that's what you're asking. You know, Lucy's got those flared ilia on her pelvis, and some have suggested that that's to accommodate a larger viscera, and that makes sense in the context of her eating lower quality foods. And then how does that affect her walking mechanics? I don't think that's been really well studied. I mean, a lot of the models that we have for walking in Lucy come from either humans or upright walking chimpanzees, and both of them are poor models to a certain extent because you've got different anatomies. So it's a good question, and I don't have a good answer for you.
One thing that might be mentioned in this context is that although the Australopithecus, the blades of the hip bones flare out, sort of sticking out sideways much more than they do in any Homo, this bending around to the front in the way that we see in modern humans is actually not seen in the archaic pelvises that we have for Homo erectus or Homo neanderthalensis.
Right. I mean, even the Atapuerca
flare.
pelvis has this incredible flare to it.
Which might suggest something about the relative recency of really serious reduction in gut size in Homo. Questions?
Regarding the expensive tissue hypothesis, if I'm not familiar with the specifics, but myosin mutation adds more into the picture in that it's a mutation that weakens our chewing musculature, and what I'm wondering is, wouldn't the fact that this mutation isn't selected against infer that there was an innovation to deal with digesting food?
Yes.
Yeah, the problem with the myosin mutation is the timing has not been pinned down. The original paper, I think, argued that it was about that this mutation occurred somewhere in the human lineage in the ballpark of 2.5 million years ago. And there have been a number of responses to that suggesting that the error bars are much larger. And we actually don't know exactly when that mutation took hold in the human lineage. But you can, in the fossils, you can see the reduction in the musculature in early Homo.
Questions?
Yeah, right here. So cooking really comes down to the ability to extra orally process food. But I mean, there's also other ways to extra orally process foods. You know, with stone tools, you could perhaps take like a tuber and put it in water and soften it up and then mash it up, or you know, mash up some nuts. Would that be enough to explain kind of the cooking hypothesis without the cooking part, and have that, and then just have cooking accelerate the process later on in the evolution of?
That's the same question I have, and you know, archaeologically, we'll try to define a protocol to work with residue analysis and try to figure it out if we can do that. But honestly, it's a big question and it's open, and you know.
So here are some important facts from modern human physiology. There's basically three categories of nutrients in the human diet that are sources of caloric energy. Okay? Carbohydrates, proteins, fats. If you try to live on proteins, it doesn't work. And the reason it doesn't work is that free amino acids build up in your tissue fluids, and they start interfering with things like neurotransmitters, and you start getting hallucinations and falling down and twitching a lot. So an all protein diet, nothing but meat, you know, sort of the Atkins diet, no carbohydrates, doesn't work. You have to get more than half of your calories from some combination of carbohydrates and fats. Now, the difficulty with, you can cook carbohydrates and make them more digestible, although I gather some questions have been raised about that lately, I've heard, but I haven't heard the questions. But there's a problem with the fats. When you heat fats, they don't become more digestible. They actually become somewhat less digestible. They undergo the first stages of things that are referred to as getting rancid. They oxygen, you know, they're oxygen combining with crucial bonds in the fat molecules, and at higher temperatures. If you look at a number of the hunter-gatherer populations that have survived into historic times and are known to ethnographers, an awful lot of their diet is coming from lipids, like the Kong Bushmen in South Africa. where more than half of the calories are coming from magango nuts that are gathered by the females, and not very much, in fact, at all from cooked animal tissue. Inuit ate an awful lot of raw fat from sea mammals, and people who try to survive on lean meat do not do very well. There's a definite serious craving for lipids in the human diet, which explains some of the characteristic profiles of Americans today. They've been putting away the lipids.
Tastes so good.
They do. They do. But there's a question in my mind about the extent to which the different components of the human diet are being beneficially affected by heat processing. And Jeremy, do you have any?
No, I think you you summed that up nicely.
Yeah.
Again, I think we can take another question.
I'm curious about the interaction of fire with some of the other cornerstones of social evolution in humans, and I'd like to explore that with you. For instance, it seems like kids wouldn't be able to play with fire, so when fire, was utilized, there was probably some type of social hierarchy or familial hierarchy. It doesn't seem like language isn't necessarily a precursor to fire, but some language would be helpful, or even things like memory. So these other components of social evolution that are key, what relationship do you think they possibly could have had with our technological advancement and use of fire?
Well, a lot of the things I just showed you, I suppose one could learn them by imitation, but there's a lot of the details about just when you stop, when the ignition point is, how long you let the fire go, what quality the smoke has to have before you stop. These are all things, it's, I guess, conceivable you could learn it by imitation, but it's a heck of a lot faster to just tell you, when it looks like this or smells like that, stop, shift the thing from the pan to the tinder bundle. I think something like this that's an essential technology would accelerate the transmission of knowledge, or if there was a pre-existing effective method of language of transmitting information, this stuff would get into it like that and be deeply impressed. In terms of social interactions, we can interact right now. You're not worried about a lion coming in that door right now, are you? Okay, your ancestors would be. Only if you had a fire there, that lion would be profoundly stupid to try to mess with you. It would be trying to attack you basically blind. The fire blinds them. So fire has a tremendous advantage of enabling people to aggregate, to interact into the night. You've been talking to someone on a telephone call. They call you and you may have won $1,000, this kind of thing. You can't see their faces, so you don't know if they're lying. Many of the clues we have about credibility or deception are visual clues. So with fire at night and someone's telling you a story, yeah, and the lion stole that gazelle carcass. That's why I came back empty-handed. That's a ticket. You could tell deception with visual clues in ways you can't with auditory ones. And having fire at night aids people to get those visual clues. So I don't want to say fire's a social lubricant because you're mixing metaphors, but it is. So there.
Whereas the heart, this home, so that's definitely.
This is one other perspective, it occurred to me as we were talking about antiquity of evidence for fire. I was thinking back to when I was a student, actually 200 meters that way. And old Professor Gabriel would say, well, the oldest evidence for fire that everyone accepts is about 200,000 years ago. All right, and then as we were studying, new evidence came out for 300,000. And also we went on further and further studies. It kept moving back and back. And if you look at the historical trajectory of research in this subject, it follows a familiar pattern. The more you look at something, if you're actually detecting a real pattern that's intrinsic to the evidence or a false one, the more you look at it, the more solid databases are. You don't get outliers and strange patterns. So what the most recent big advance has been a switch from evidence of fire being about 300,000 years ago to being about 800,000 years ago. And there are a few of these outliers, about 1.5, 1.3. Van der Werk is currently an outlier, but it's in a cluster of outliers at about 1.2 million, 1.5 million. So I would predict that this trajectory of leaps followed by filling in of clusters of outliers will continue. And if the fire hypothesis, fire and diet hypothesis, the cooking hypothesis is correct, These outliers, we'll probably see a bunch of outliers around 2-point-something million years ago, and then those outliers will fill in as a cluster. But if we don't, that's that's a falsification of the hypothesis. It's an hypothesis. The more you look, the more the data, if it's correct, the more the data should fit the pattern. If it's false, the more the data should diverge from the pattern.
Hi. So I have a question that's more in logistics about finding fire outside of a cave. Because it seems like inside of a cave it's a little easier to tell if there was fire being used. But in terms of ash deposits, how do you locate that? Are there like particular sediments that just take care of it better, or how exactly do you find it?
In such open-air sites as I've been involved in, you look for burnt flints.
So rocks that have thermal damage of the sort Francesco discovered. We call these fractures pot lid fractures or crazing fractures. If you find a cluster of those together, sometimes you're looking for oxidation of the iron in clay. Many clays have lots of iron in them. You look for those two things occurring together. In such clays, you might look for carbonized plant remains that have been enclosed and baked into the clay, much like temper is baked into pottery. So, but you have to remember, at open-air sites, there's a lot more potential sources of destruction. Yeah.
In burnt flints, can you use thermoluminescence dating to determine exactly how long ago the flint was burned?
Exactly, and if it's in the range, because it could saturate, but also you can get information how hot the flint went. But the best situation is the Pompeii situation, and just you have to keep excavating. We'll find, and it's just a big puzzle. Try to put it together and.
We have a term.
Sure, go ahead.
We have a term in archaeology called middle range theory, or middle range research. It's how we know what we think we know. And this involves going out and observing how the archaeological record forms as a result of living humans' activity. Now, obviously, if we're trying to find these things in the past and recognize them, we need to find out what's the persistence, what influences the persistence of fire in different kinds of geological substrates, so caves versus open-air sites. If you find a hearth, what's the probability of finding that? Can you miss things? Can you miss a substantial fire? A couple of years ago in Ethiopia, we found Richard Leakey's camp from 1967. We found tin cans and bottles and this kind of thing, and not a single trace of fire. We know they were camping there for months and months and months. Where's the fire?
Did you use micromorphology?
No, we used their noses. I think what he was doing is burying the ash or something like this, as is a good camping practice. But if young people want to make contributions to this, what they need to do is go out on a landscape where people use fire habitually and move around a lot and see if mobility, if staying in one place versus moving habitation sites, what does that influence? What does the different kind of fuel matter? Can you detect a fuel by one kind of wood versus another kind of wood? Does it have differential visibility? We need, if you want to know what you think you know with confidence, you need to know how you know what you think you know. I got that right?
I guess. I don't know. That's middle range theory.
Always look for a tephra, and then go under the tephra, and you'll maybe find.
Tephra is an ash fall?
Yeah, ash.
Yeah.
Ash. Sorry, I'm a geologist.
So I have a question. Does the antiquity of zoonoses, that is to say, human diseases that are produced by carnivory, like tapeworm infections and so on, does that tell us anything about the antiquity of habitual meat eating?
If we knew it.
Well, there's some work on that, right? On the introduction of tapeworm that goes back about 1.5 million years. It was originally thought to be the introduction of agricultural animals, is my understanding, because the tapeworms that were associated with humans were coming from cattle and pigs, but it turns out they're coming from kudu and warthogs back 1.5 million years ago. And there's evidence of a South African Australopithecine that may have had brucellosis, which is another of these diseases you can get from meat eating. And that's the 2.5 million year old big male, the
Raw meat.
STW 431.
Raw meat.
Raw meat.
Raw meat.
Yeah. But there's some other folks think it just had osteoarthritis. So it's difficult to
But you can get tapeworms from eating cooked meat if it's not properly cooked.
Cooked, yeah.
Are there any other questions? We've got time for a couple.
Is the use of fire and how it's been passed on, like, was that mainly for cooking, or was it more for protection, or both, or not known?
And how would you tell?
Well, I mean, because like
No,
when you
I-
showed the methods and you said the most basic would be just to take 2 sticks.
Yeah.
How long would that really take?
How long did it take to learn it?
No,
Oh.
to make the fire. Like,
Oh, just with this or the Fireboard. The fire saw, which I didn't demonstrate because it involved even more labor. 20 to 40 minutes, depends on the wood. You know, with bamboo, you can get just like that. You know, watch Survivor on TV. This is the technique they all learn before they go on the contest because they put them on islands in the Pacific all the time now. If you've got bamboo, not a problem. You can make fire very, very quickly, provided you understand that friction and it generates enough heat, drops the sawdust into a combustible source of fuel, and you're good to go. There's very few places on Earth you can put yourself without the materials to make fire. Basically, the high Arctic and Antarctica, and maybe at the top of a few mountains.
because I thought if they made the fire just for protection or for eating cooked meat, I guess with the costs and benefits, like, wouldn't the cost of like the time consumption and energy that's used not be worth the advantages?
But this is it. But people don't think. We always think about the benefits, but you know, the costs are considerable. It takes a lot of energy, it takes a lot of time, it takes a lot of transfer of knowledge to maintain it. It takes practice. It takes fuel. In parts of the landscape where people have been living and using fire for a long, long period of time, there's no fuel anyplace. They've stripped the landscape bare and they're burning goat dung. You know, see most of the Middle East and North Africa. Good thing they have oil.
But if you know, you talked about the cost of knowledge, but if one of the side effects of having fire is being able to have a brain that's 3 times as big as it would be otherwise,
It's worth it.
then the cost of knowledge is more than offset by the ability to have the knowledge in the first place as a result of.
No, you think about something that's as polyvalent and useful as fire. You can deter carnivores. You can increase the length of the day to interact. You can cook food or not. You know, you can cook some food and not some other foods. You can detoxify some foods and others not. It's a valuable thing to share, so it's a social, it's a a bonding thing among societies. It's potentially a very valuable thing, but it's not just one thing. You know, we use one term for it, but it has many, many possible implications.
So there's been a lot of work done on the anatomy of the hand and how the changes in hand anatomy have been functionally related to stone tool construction. It seemed to me that you're making the fire right there was more labor intensive than making a stone tool.
Oh God, yes. You can make stone tools in seconds.
So it's, you know, and given the potential benefits of fire and how difficult it is to make the fire, it seems like it could be a logical next step to say that there should be some anatomies that we may pick up that allow you to be better at that.
I have all kinds
So
of
what-
people ask me, you know, can we measure this and that, about stone tools? And I said, sure, you know, I like any excuse to make stone tools or get paid for it. I'm all in. But you know, there are a lot of people who know how to do this far better than I do. If I were interested in the origins of fire, I'd look to see if there's something about any of these techniques, either this technique or this one, that leaves a anatomical mark. I don't know if it does. Like I say, I just make the fires. I don't study them.
Any other questions? Well, if not, then I'm going to thank you all for having come here today and for listening to us and for asking penetrating and interesting questions. I'd also like to thank the people who make these dialogues possible. The director of BU Productions, our video production team, Nancy Mars, other people from BU Productions, Phil Zikos and Mark Helton. I'd like to thank our web wizard, Cuckoo Dalio, for supervising and making possible the webcast that we always begin these dialogues with. And especially I would like to thank my colleague and partner, Kay Brown, who is responsible for having cooked up these dialogues, for thinking of most of the bright ideas that go into making them work, and for being in charge of the production values that make them successful. So let me wish all of you a good evening, and there you will find, if you go out in the foyer out here, there are some nutrients that have been processed using heat that you will find digestible and that we would like to share with you, being as we are human. Thank you very much.